Hello and welcome to the very first lesson of Area of Study 2 within Unit 3. This unit focuses on the generation and transmission of electricity, and we're going to start off with a lesson that is not exactly specified within study design. However, you do need to use the stuff from this lesson in the rest of the study. So this may be for some of you a bit of a revision of 1-2 physics. However, there are some little bits that you may find anew. So what are we going to have a look at? We're going to look at, well, what I would call the principles of electricity. Those are voltage, current, resistance, and power. And within those, we're going to have a look at series and parallel circuits. So a lot of the work today is going to revolve around circuits. So why are we doing this? Well, we need to understand each of the 4 key elements, so voltage, power, current and resistance, to understand DC and AC power, pretty much. We're going to need to use this knowledge when we come to transmission lines, to transformers, and we need to make sure that we understand that. Otherwise, we don't really have much of a hope for the rest of this area of study. So start off with voltage. We look at it in area of study 1 from the point of view of looking at it as charges, but now we look at it from the perspective of power generation, and with power comes current. So current and voltage is very, very closely linked, and that while we have another definition which leads to the electrical potential difference as kind of an alternative name, we don't really think of it like that anymore. We consider something called a voltage drop, which is the difference between, or the potential difference between 2 points. And we'll see that on the next slide. You can see here that between A and B, there is a difference, and that difference relates to the resistor. So the resistor there is in white. It can be whatever color, but it's always usually indicated by a rectangle or square or something, or potentially some squiggly lines, and we may have a look at that in another lesson. So if we look at this circuit, and we assume that there's no resistance in the wires, this will be the case for this lesson. We'll always assume that there's no resistance in the wires. When we get onto transmission lines, that's a different story. But we know that there's a voltage drop. There's a difference between the voltage in one section and another section, because on one side of the circuit, we have 12 volts from a battery, but we've got no supply on the other. And every circuit has to balance. So if we divide this very crudely in 2, there's 12 volts on this side, and that means that somewhere along here, we lose 12 volts, and that 12 volts belongs to this resistor. So there's a voltage drop of 12 volts, because 12 volts is kind of consumed by the resistor. We're going to bring in Kirchhoff's voltage law, because this really goes to explaining from a scientific point of view this kind of observation. So if we went back here, you can see I kind of divided in 2, but what Kirchhoff says is that any 2 paths from one node to another node, so the nodes in this case are going to be X and Y, that's what I've called them, and between those 2 points, whatever path you take, you're going to observe the same voltage drop. So whether that's 12 volts through the battery or 12 volts through the resistor, it doesn't matter. There's still 12 volts all up. And this idea can be very, very useful when we get into circuit analysis, and we'll see that a bit later on. Current is the flow of charge. And obviously it's the flow of charge with respect to time, because that's how we measure flow. So it's the amount of charges where we consider a positive charge to be kind of the direction of a conventional current, or by contrast, we can say that that's the same as the negative charges moving in the opposite direction. So those two ideas are the same. We will always consider current to be the flow of positive charges, even though we know that electricity is really the flow of electrons. So even though there's an apparent contradiction there, this is the convention, and we will always use this throughout this area of study. We usually indicate it on our circuit by an arrow on the wires itself. So you can see that I've popped an I representing the current with an arrow. It's measured in amperes, which is one of the 7 fundamental units. And we've already used current when we looked at the likes of DC motors. As another reminder, conventional current is the same thing as the flow of positive charges. So that means it goes from the positive terminal of the battery all the way around to the negative charge, or the negative end. We also assume that current doesn't change when flowing through this resistor. So the current's constant throughout. That may not make a whole lot of sense, but it does make sense as we get on, because if it did change, then we would end up with some issues. So we assume it's just constant. Resistance, and there are lots of jokes about resistance because the unit is in ohms, but that's something for you to laugh at in your own time. It absorbs voltage, and it does something with it. So it'll typically turn into heat, and that's what a resistor usually does, which is why, for instance, your computer, my computer right now, is getting quite warm because there's some kind of resistance there that the battery is providing to the computer, and the resistance is kind of, I guess, equated to heat. So there's kind of an example there. When we think about resistance in a circuit, you need to come up with a way of making everything equal to one resistor. Otherwise, our calculations become very difficult, and we'll see that with the series and parallel laws in a moment. It is important to know that every single circuit has to have a resistance, because otherwise we would have an issue that the current and the voltage that matter would be infinite. So, as foreshadowed, the series law. Well, what is it? It says that when we have something in series, which means that it's connected in a continuous line as opposed to lots of separate paths, then the total is just simply the sum of them. So R1 plus R2 plus R3 plus R4, etc., etc. That means that we can draw an equivalent circuit with a resistance of RT rather than 8 separate resistors as we have on the right. We can do something similar, but not exactly the same for parallel. And it is important when you're working with circuits to note whether you're doing things in series or parallel or a mixture of both. There are junctions, and by that I mean these things over here. Here is a junction, it splits off into separate paths, and then it comes back together at these points. So all 3 of these on the top and the bottom could be joined. So let's say that instead it went to here, this went to here, this went to here, means the same thing, because there's still a junction. Just because I've represented it this way doesn't mean that there are other ways of representing it. The resistance, the total effective resistance, is the sum of the inverses inverted. And by that I mean you do 1 on R1 plus 1 on R2 plus 1 on R3. And then when you raise all of that to the power of -1, you get the total resistance. And that is what we have there. Should note that in parallel, your resistances should get smaller than in each of the independent resistors, whereas in series they should get larger. So there's a bit of a hint as to what happens. So when we work with voltage, and we do it in series and parallel, voltage gets split up when you're in series. So it would be a direct fraction of the total resistance. So for instance, the voltage through the voltage used up or dropped through the first resistor, R1, would be R1 over R1 plus R2 plus R3 multiplied by the input voltage. So say it's a 12 volt input. Each of the resistors is 2 ohms. Then resistor 1 will take 1/3 or 2 over 6 of the input, which would mean that it is 4 ohms. Or sorry, the voltage drop would be 4 volts. There's still 2 ohms in the resistor. Parallel voltage is the same throughout everything. Current is the direct opposite to that. So current is the same through in series, but it splits up much like it did for voltage in the previous example for series. So that's the distinction of how we treat voltage and current. And it is very important to remember these, otherwise your circuits will end up as one large mess and they will have lots and lots of errors in them. Nevertheless, we have a circuit here, which I have annotated, I suppose. We know that the voltage into the battery is going to be nothing. The voltage out is going to be 12. The current's going to go in a clockwise direction. And when it passes through the resistor, all of it, all the voltage will be used up. So you obviously don't have to write all of this on your circuit, but it is quite important to write down pretty much everything you know, and that will help you get through the question. Now we move to power, which is a little bit separate from voltage, current, and resistance because it considers both voltage and current as together. So the higher the voltage times the current, the higher the power. And that's quite literally the formula. So P equals to VI. Measured in watts or joules per second. And you could figure that out using some fundamental unit analysis if you wanted to prove that those two things were the same. When we think of power, we often think of it as a bit like momentum. So instead of mass times velocity, it's more charge, being the current. More charge would be the voltage, and the fact that it's going faster means that the current's higher. So that's how we think of it, and those two diagrams there kind of illustrate that. You can rearrange your formulas for V and I, but you have to be very, very careful because in some situations you'll end up finding a result that isn't the correct one. So if you don't pick the correct current or the correct voltage, or for that matter, the correct resistance, then you will end up with results that that are incorrect. So when we put it all together, we have 4 formulas. You've got your series and parallel laws, and then your kind of more broader laws relating voltage, current, resistance, and power. And each of those units are shown there. We'll move on to a practice question. Very first one, calculate the conventional current in the circuit and state its direction. A couple of marks, should definitely not take you any longer than 2 minutes. So have a go at that. All right, now that you've had a go at that question, what is the solution? Well, very straightforward. Use V equals to IR. You substitute in all of your numbers. You've got 12 volts, you've got 24 ohms of resistance, and you get half an amp as current. The direction is going to be anti-clockwise because conventional current is the flow of positive charge. So that means it's going to go from the positive charge all the way around like so. Practice question 2. This will require a bit more thinking, a bit more practice, putting those formulas into use. So draw a labeled diagram of an equivalent circuit that contains only one resistor. Each resistor in the diagram has a resistance of 4 ohms. So this may require a bit of thinking just to get started, but it shouldn't take you too long. You've got 3 minutes to do 3 marks. Okay, now that you've done that question, hopefully, what is the answer? Well, to figure that out, we need to first use our series and parallel laws, and then we'll see what happens. So the 2 blue resistors, which kind of form a sub-circuit of the circuit, we have to apply the parallel law because they are in parallel. So each of them is 4 ohms. So as per those calculations there, 1 on RT equals a quarter plus another quarter, which is a half. So the total effective resistance of those 2 blue resistors is 2 ohms. We now have 2 green resistors, which are each 4 ohms and an equivalent to the blue ones of 2 ohms. So those will all be in series. So now let's just say ignore this one. This one becomes 2 ohms. Each of these are 4. And we can apply our series law, which just says add them up and you get 10. So nothing too dramatic in terms of calculations there. And then you draw something like this. You'd probably also include the direction of the current, which would be that way. You might label, so already you've got the resistance label there. You weren't given a voltage, so you don't have to worry about that. Mark allocation, you'd get 1 mark for doing this section for the parallel, 1 mark for doing the series calculations, and then 1 mark for your final drawn diagram. So that's how that would work. Let's take a look at 2B. So given that the battery supplies a voltage of 30 volts to the circuit, calculate the current passing through the resistor in your answer to part A. I might go back very quickly so you can remind yourself of what that circuit looks like, but otherwise you're given the voltage now of 30 volts, so you can have a go at that question. Okay, now that you've done that, hopefully, again, much like most of the things within this unit, the calculations won't be too difficult. So you've given the voltage, you've calculated the resistance from part A, put that into your formula, and you get a current of 3 amps. So that's the diagram there if you wanted to have that down. But the 2 marks come from the recognition, kind of the first 2 steps, and the current, your answer, of 3 amps is the final mark. Next question, calculate the power in the circuit. So it's worth another 2 marks, probably a little bit generous, this mark allocation, but physics as general is quite generous. So you can have a go at this question. All right, now that you've hopefully done that with a reasonable level of confidence, let's see what the answer is. We use our formula for power, voltage times current. We cherry pick our answer from the previous question of 3 amps and the voltage from that, which is 30, and you get 90 watts or joules per second. And that's that diagram there, if you find that useful to visualize. Now comes slightly more difficult. Find the voltage and current passing through each blue resistor. It's worth 3 marks because it will require a bit of arithmetic, but I think that you can do this within 3 minutes. All right, now that you have hopefully done that question, how do we go about this? Well, we kind of have to undo the process that we got to get an effective resistance of 10 ohms. So we know that there's a voltage drop of IR over each resistor, and we know that over the first green resistor, which is 4 ohms, it's going to be I times R. Resistance there's 4 ohms, the current's still 3, so we get 12 volts. So 18 volts kind of left over. That's kind of not that useful in some ways. Over our last green resistor, we've also got a voltage drop of 12 volts because the current there is still 3, because remember in series, the current doesn't change, and the resistance is still 4. So there's another 12 volts there, which leaves us with 6 volts left over. And you could calculate this if you had if you knew already, as you probably did, that the resistance of the 2 blue resistors together combined was 2 ohms. So you could do V equals IR, you'd get 3 times 2, which is 6 volts. Or you could do 30 minus 12 minus 12, which is also 6. So there are 2 methods for going about that. When it's in parallel, voltage doesn't change, current does. So 6 volts are delivered to each blue resistor. And what we can do is that the 3 amps into the junction, so into point over here, get rid of that funny mark over there. So you get 3 amps delivered to that junction. You also get 3 amps out. That's just how it works. But our I equals to V over R can be applied. So we get 6 volts over a resistance of 4, and that gives you 1.5 amps for both resistors. Hopefully that makes sense. There are other ways in which you can do this, but the key takeaway is that in each of the blue resistors, you get 6 volts and 1.5 amps. As a quick reminder and summary, our current in parallel is proportional to your individual resistor over the total effective resistance in parallel, and then you multiply that by the current of your single equivalent resistor, or you could have done IT. I could have simplified that expression a bit, and the same but in series is true for voltage. So those 2 things you may wish to write down. We will finish up there because there's a lot of stuff in that lesson. We had a look at the basics of electricity, so voltage, current, resistance, power, and we looked at the series and parallel laws. Next lesson, we'll be taking a look at flux, and then we'll move into the application of flux, which is in part, I suppose, Faraday's law, Lenz's law, and induced current kind of fits in with both of those. So thank you very much for your attention this lesson. Hopefully you found it interesting and you learned something new. If you want to get in touch, you can head to airlearners.com and you can find me on the tutors page. Otherwise, that will do for today's lesson. I'll see you next time.